start this up here. I just sent an email about Thursday. I have an appointment that I need to attend, so I moved it to 5:30. Now, understandable, if it doesn't work for you, that's okay, not a problem, you can't attend. But I'm gonna do 5:30 to 6:45. So only for Thursday. And if you can't make it, no worries. I will record this as usual and you can view it later on. If no one shows up, I got nothing to say, I won't record anything. I direct you to my 1 o'clock class, which I just got done, and that's being uploaded, so you can view that one. Or alternatively, as you know, on the course website, we have other recordings for the chapter to look at. Okay, so just to let you know. So hope everyone's doing okay. What I want to do is share the screen here to go to the course calendar, so we can kind of give you a heads up of where we're at. Today's the 15th. We should finish chapter 5 today, and Thursday obviously kick into 6. 6 is very short. It's gonna, I think it's like 25 slides, talks about the periodic table. It's very quick, so we'll probably have that knocked out pretty quick. Point being that we have on the 29th the next exam scheduled. That's for chapters 4 through 6. So we should be done with those 3 chapters way before the 29th. I sped out the homework to give you plenty of time. That homework is flexible with respect to due date. I can adjust them. I always will give you at least a couple of days after we finish the chapter. These early chapters, or the chapters we start getting into now, pretty short, so you got plenty of time later on. It might take 2 sections to do a particular chapter. I'll make sure I give you plenty of time to finish that homework and so forth, including the activity. But the exams are pretty much etched in stone. They're given to all the 130 students at that time period. Anyway, those of you, I did open up the exam. I hope you went in there and took a look at your answers. If there's a question, you're concerned about it, shoot me an email. I'll go over it, look at it. Definitely give you the points if if you're correct. I don't have a problem with that at all. So anyway, let us begin where we left. Okay, and we were talking about electrons, and it kind of surmise where we're at this point up to now. We had started talking about the atoms. We started talking about how the atom is put together. We talked about the nucleus, the proton, and the neutrons being a nucleus. But at that time, we knew the electrons were somewhere there, but not quite sure. More research came into play, and came to realize that these electrons are actually in distinct energy levels. And not only being in distinct energy levels, they are in what we call orbitals. Now, to refresh your memory, there's only 4 types of orbitals, with the letters starting with the letters S, P, D, and F. Okay, 4 types of orbitals. And we got into writing the electron configuration, and that's just to demonstrate where these orbitals are, to give you an idea about where these valence electrons are, because that's where all the action's happening. That's where all the chemistry occurs, on these valence electrons. Now, let me refer you to the periodic table real quick. This periodic table, we can gather this information very quickly, okay, with respect to valence electrons, but only with respect to those electrons under the Roman numeral 1 through 8As, okay? And so everybody in group 1A, which is the far left, has 1 valence electron. And let me point out something real quick. Now, everybody here, I missed hydrogen. Everybody here has 1 valence electron. And so lithium has 3 total electrons, but of those three, one of them is in the outermost shell. That is the valence electrons. And so if we look at group 7, way over here on the far right, which includes fluorine on down, they are in group 7, Roman numeral 7, okay? And what that tells us is that there are 7 valence electrons for all of those in that group, okay? And so because they have the same number of valence electrons, they all have similar reactivity, very similar reactivity. So everybody in group 3 would have 3 valence electrons, okay? And so if you're given any element in here, with respect to the A elements, okay, you can very quickly determine how many valence electrons there are simply by its position in the periodic table. So let's go back to the slide. I will be referring to that periodic table quite extensively because it's going to give you a lot of information. So if we look at chlorine, chlorine is in group 7, okay? That being said, it would have 7 valence electrons. Beryllium is in group 2. It would have 2 valence electrons. And aluminum is in group 3, which tells you have 3 valence electrons. The electron configuration is denoted here, for example, 1s2, 2s2, 2p6, 3s2, and 3p5. The third energy level, that is the most outermost shell for chlorine. And notice I'm calling this chlorine because we're going to give it a different name when it becomes what we call an ion. Okay, so that is where all the chemistry is going to occur, on the valence electrons. And what it boils down to is that an element is either going to gain electrons or lose electrons. And it's striving to obtain that magic 8 number. And you can see chlorine is 3s2, 3p6. The p orbital has the ability to handle a total 6 valence electrons. So with that in mind, you can look at the electron configuration and predict that it's going to gain 1 electron. And that's the case, it does. With respect to beryllium, its outermost shell is in the 2nd energy level, okay? And there's 2 of them. Now, there's also another orbital in the 2nd energy, and that's the p, the 2p. Now, beryllium has the capability to pick up 6 electrons, but think about it from an energy standpoint, okay? Think about it. Does it make sense that beryllium would want to pick up 6 or give up 2? From an energy perspective, it would be much easier to give up 2 than to gain 6 to get that magic 8. On the contrary, with chlorine on top, it has 7. Again, it would take a lot of energy to remove those 7, but not so much energy very easily to pick up 1. Now note the difference between the chlorine and beryllium. Chlorine is a nonmetal, okay? And beryllium is a metal. And I may have stated this before, but all metals, put this in your long-term memory, all metals want to lose electrons, okay? And all nonmetals want to gain electrons, And if we look specifically, going back to the periodic table, if we look at all of the nonmetals that normally we're going to deal with the majority of the time, is wrong one. Let me get this one here. You know, we're looking at bromine through fluorine, phosphorus through chloride, chlorine, selenium to bromine, and iodine. Okay, they are very close to the noble gases compared to these metals on the far left side, and I'm talking specifically with the A elements. They're far away from those noble gases, okay? And so these non-metals, just by the nature of the beast, want to be, with respect to electron number, like the noble gases, because that by gaining electrons, they pick up 8 electrons totally. Whereas the metals in the far left, by losing electrons, they also become the octet, but not on the outermost valence shell, but the next one in. And we'll have more to say about that here in a second. All right. And so you can use with respect to valence electrons, and only really for the A elements, the group number that they're in, to help you determine how many valence electrons they have. So everybody in group 1A has one valence electron. The ones, lithium has 3, potassium has 19 electrons. They all differ in the number of electrons, but they're all similar because their outermost electron number is 1. Shooting to 2A, we have 2 valence electrons, so forth, 3A, 3, and 4, etc., until we get across the periodic table into group 8A, and it has 8 valence electrons. And those are where the noble gases are. Those are the ones that are very inert and unreacting. They all have 8 with the exception of helium. Remember that. Helium, He, does not have 8. Helium only has 2 electrons. Its atomic number is 2. It's only got 2 electrons. So helium's rule is the duet. All the other noble gases is the octet, striving for that 8 number. Okay? And so we can use the periodic table, and we can see that strontium has 2 valence electrons just based on where it is on the periodic table, and that is number 38. Bromine on the far right, which is number 35, has 7 valence electrons. If you have your periodic table, you can use that as you go along. Argon is in group 8, has 8 valence electrons. Silicon is in group 4, has 4 valence electrons. And sulfur in group 6, having 6 valence electrons. Don't confuse valence electrons with the core electrons. They all have a total number of electrons. The valence electrons are the outermost shell, okay, the outermost set of electrons, and the core are the ones inside, however number they have, okay? So, how do atoms make compounds? Now, we've been talking about the atoms now, right? And now we're getting into what's going on with these things as far as how do they get together to make compounds? How do they bond? Okay. Thing to remember here is the driving force is to get an octet around the nucleus, and to get that, you're either going to gain electrons or lose electrons. Okay. Someone at 1 o'clock asked me a question about the metalloids. What happens to them? I said earlier, metals lose electrons, non-metals gain electrons. When it comes to metalloids, it depends on the reaction conditions. I can't give you, yes, they always gain, no. Depending on the conditions, they can do both. Remember, metalloids have the property of metals and non-metals. Okay. So, the drive is, yes.
Sorry, did you say, can you repeat that one more time? You said non-metals lose, or
yes.
do they gain?
No, non-metals always lose electrons. Put that in bold print. Okay.
Okay, and then the metals gain.
You know what I did? I got disrupted. Reverse that. My apologies. Metals lose electrons, become positive. Non-metals gain electrons. Okay. They want to be more like the noble gas. And I'll give you an example here how that works. Okay.
Okay. Thank you.
Sure. Okay. Let's take the electron configuration of sodium. Okay. And I'm going to have another technique to how you can write the electron configuration using the periodic table very quickly. That's correct, Nathan. The metalloids, semi-metals, depends on their reaction conditions. Okay. All right. And so let's take a look at sodium. Sodium element has 11 protons and 11 electrons. Okay. Now, its electron configuration is 1s2, 2s2, 2p6, and 3s1. Sodium is in group 1, okay, has 1 valence electron. That highlighted 3 tells you sodium is in the 3rd energy level, and it has 1 valence electron in the s1 orbital, okay? Now, what happens again, like I said earlier, the 3p orbitals are there, but they're empty, totally empty. And so the question is sodium want to gain 7 electrons, or can it lose that 1? And like I said, it's a metal, and metals want to lose electrons. And it's going to lose that 1 electron sitting out there in the 3s orbital, okay? And when that happens, that orbital becomes empty now. And so now the new electron configuration is 1s2, 2s2, 2p6. The new valence electron for losing, the new valence valence electrons are right here. It used to be when sodium was a metal, an element, the valence electrons in the 3rd energy level. But in losing that, the next layer of the onion, so to speak, if you think about it, is the next layer. First layer has been taken off, it's empty. We got the next layer in, well, it's full. It is full because it has 2 electrons in the s orbit and 6 in the p orbit for a total of 8. So you can see by losing an electron, the octet has been fulfilled. Now, why does it have a positive charge? Well, give it a thought here for a second. We start off with 11, sodium metal has 11 protons, which is positive, 11 electrons, which is negative, so our net charge is 0, okay? When it loses 1 electron, it did not lose the protons, remember that. Protons are not lost. If you lose a proton, you create a whole new element. Protons define the element. And I mentioned before that you can lose and gain electrons and neutrons all day long, and you don't change that element. So we didn't change the protons. All we did was lose 1 electron, so now it has 10 electrons or 10 negatives. So what is the net? I got 11 positives and 10 negatives. Our net is a positive 1, hence we have what's called an ion. Okay, and we put in superscript plus 1 in superscript to designate sodium as an ion. That is what we ingest when we put this sodium chloride in our French fries. We're not ingesting sodium. If we did, we have a big trouble because sodium metal is extremely reactive and hazardous. So we are ingesting the sodium ion. And the ion is nothing more than that element, specifically sodium, that lost an electron. Okay, now let's take a look at sulfur. If we do the electron configuration of sulfur, we know based on the periodic table, sulfur is number 16. It has 16 protons and 16 electrons. Its electron configuration is 1s2, 2s2, 2p6, and then 3s2, 3p6. Now, we know that sulfur is in group 6, okay? And the valence electrons are, we got 6 of them. Remember, the superscript designates a number of electrons. 2 of them are in the s orbit, and 4 of them are in the p orbits, okay, for a total 6. Now, it's a non-metal. It does not, it has a tendency to gain electrons because if you think about it, I got 6 to start off with. Now, energy perspective, I'm striving for 8. Is it easier to lose 6 of them or just to pick up 2? Well, from an energy perspective, picking up 2 is a lot more energy favorable. And that's what happens. It picks up 2 electrons because the p orbit has spot for 2 more electrons, okay? Because we can put a maximum of 6. And in doing so, now it has same number of protons, but now it has 18 electrons. And our net charge is a -2 because I got 16 positives and 18 negatives. Mathematically, I got a net of -2. Hence, we put in superscript -2. Now, it doesn't make a difference if you put 2 minus or -2, it's the same thing. Okay. And now look at the valence electrons for the ion. It's still on the third energy level, but it's full. I got 8. So I fulfilled the octet rule, okay, by gaining electrons. For the metal, I fulfilled the octet rule by losing electrons, okay? The driving force is that octet. How do I get to it? Can I lose it or gain it? Now, how do we write the electron configurations? Well, you see some more examples here someplace somewhere, homework, exams, activities, things like that. But when you look at that, you see K, all right, you know K is potassium, but don't forget to look at that superscript. That superscript tells you it's the ion. It's a +1, plus it's a metal. So it lost an electron to give me a +1, okay? And so I write the electron configuration. I could start off with writing the configuration for potassium element, and then realizing I'm working with the ion, take out the 1 valence electron, and I have the electron configuration for potassium ion, okay? So, which becomes 1s2, 3s2, 2p6, 3s2, 3p6, okay? Because potassium's in group 4. The electron that lost came from 4s1, okay? Now, potassium started off with 19 electrons. When it became an ion, it now has 18. It has the same number of electrons as argon, okay? It's not argon, I overemphasize that. Potassium ion did not become argon. It became similar with respect to electrons as argon. There's a big difference. If we look at nitrogen, which picked up 3 electrons, its electron configuration now is 1s2, 2s2, 2p6, okay? Nitrogen by itself would have been 2p3, but picking up 3 electrons, now it has a -3. Now it is electron count like neon, okay? And magnesium losing 2 electrons, now its electron configuration is also like neon, okay? So if you look at the periodic table, when we look at metals and they gain electrons, they become what we call isoelectronic. They have the same number of electrons as a noble gas in front of it. So when fluorine gains an electron, it's now isoelectronic with neon. The same would be true with nitrogen and oxygen. When nitrogen, oxygen, and fluorine become ions, they are isoelectronic with neon, okay? When phosphorus and sulfur and chlorine gain electrons, they become isoelectronic with argon, okay? Now, if we look at the metals, like say sodium has 1 valence electron, when it loses an electron, it becomes isoelectronic with the noble gas behind it. So sodium ion becomes isoelectronic with neon. Lithium, when it loses that 1 electron, becomes isoelectronic with helium. Potassium, when it loses that electron, becomes isoelectronic with argon. Okay, because they end up with the same number of electrons when they become ions. Let's go back to this. Okay, and so not only would the group number tell you how many valence electrons it has from the periodic table, but it also would tell you what kind of charge it has when it becomes an ion. Okay, and so group 1 has 1 valence electron, will have a +1. Group 2 with 2 valence electrons, because they're metals, will have a +2. And when we go across, go up to group 3 or the metals, they will have a +3 charge. Okay. When we go over to groups 7, they want to be like noble gases, so they're going to pick up 1 electron, so they have a -1. Group 6 will have a -2, and group 5 will have a -3 with respect to their charge. Okay, so nonmetals want to gain electrons, become negative. They have a special name for them. We call them, right now I've been calling them ions, but to distinguish them even further, we have a special name for the type of ion. When it gains an electron, that ion is called an anion. So if you read about an anion, you're talking about a negative ion, which means it's an element that gains an electron. Okay. So group 7 becomes -1, group 7, -1, group 6, -2, group 5, -3. Now you might ask about group 4. Okay, group 4 is a little bit special. Group 4 is these guys in here. Now, they're special because they have 4 valence electrons. And so they're like on the fence. Depending on the reaction conditions and what you do to them, they can either gain 4 electrons or lose 4 electrons. Because having 4 valence electrons and energy, from an energy standpoint, just as much energy to pick up 4 as it is to lose 4 of them. And so depends on the conditions. We can't really predict what charge they will have when they become ionic, but it depends on the conditions. Carbon, for example, can easily gain 4 electrons. So I give you a -4. It can also lose 4 electrons to give you a +4. So those guys in group 4 have a range of charge that they can have. Can go from a +4 all the way to a -4. Okay, so metals lose electrons, we call them cations. Okay, nonmetals, we call them anions. That's how you distinguish what type of ion you are working with. And what about group 4? Well, just simply like I just stated, they have the capability of going to a +4 range or all the way to a -4 range, depending on the conditions of the material. And obviously we know now that group 8, that they're stable. Their octet is fulfilled, hence they're called noble gases. Okay, so going across the periodic table for the A groups only, the B groups we can't predict as much as we can for the A ones because it depends on the conditions. For example, copper is in the B group elements. They have a special name which we'll learn later on. Copper can exist as either as a +1 or a +2. Iron, we're all familiar with iron, can exist as either a +2 or a +3. So the conditions vary. So we can't predict too much with the Bs. But with the As, going across the periodic table from left to right, all the metals will have a +1, +2, or a +3, depending on what group they're in and how many valence electrons. The elements in group 4, again, can vary from +1 to -4. And then across the board, we get -3, -2, -1, and eventually to the noble gases that have a 0 charge across. Okay. So our fence is group 5. Anything less than group 4, they lose electrons, have a positive charge. Anything greater than group 4, they gain electrons, end up with a negative charge. Okay? And so how do we figure out the charge for them? Well, here's lithium. We look for it in the periodic table. Okay, hopefully you're familiar with the name lithium. You can find it in the periodic table. It is element number 3, and it is in group 1. Being in group 1, okay, it will have a +1 charge when it becomes an ion, or in this case, a cation. Magnesium is in group 2, it would have a +2 charge. Sulfur, being in group 6, will have a -2 charge. Bromine will have a -1 because it's in group 7, it's going to gain electrons. Nitrogen, being in group 5, it's a nonmetal, it gains electrons. And then aluminum, being in group 3 and being a metal, it is a +3. Now, I'm going to introduce you to a little bit of a naming here because we're going to be using that quite a bit. There's a chapter called nomenclature, which is just a fancy name for name that count. Now, when we name the ions, the positive ions, the metals, we keep the name as is. Lithium went from lithium element to lithium ion. Magnesium element went to magnesium ion. So if we want to describe the ion for a metal, we just tell it it's an ion. The nonmetals, we totally changed the name. We got the name sulfur. When it becomes an ion, the name is totally changed. Oh, you have a question? It is correct, Nathan. You gain an electron, either 1, 2, or 3, you become negative. The magnitude is dependent on how many electrons you gain, -1, -2, and -3. And if you lose electrons, you become positive. Again, the magnitude is how many valence electrons you have, so it can go from a +1, +2, +3. Okay. Now, sulfur, that is the name of the element. But when it becomes an ion, the name changes to sulfide. Okay? Bromine, that's the name of the element. When it becomes an anion, it becomes bromide. Okay? Nitrogen is the name of the element, and when it becomes an ion, that's right. Okay, so in essence, the nonmetals, we change the suffix. So sulfur, we drop the UR after the F, and we add the IDE. Bromine, we drop the NE and add the DE, call it bromine. So you have fluoride, chloride, bromide, iodide, okay? Now, what about oxygen? What do you think its name gets changed? Well, first of all, oxygen itself. What kind of charge does it have when it becomes an ion, an anion specifically? Because it is in group 6 and it's going to pick up 2 electrons, right? So what kind of charge does oxygen have? Anybody want to take a guess? Don't guess. You should know this just by
Be -2, right?
negative. You broke up.
-2.
Exactly. And the name, it goes from oxygen when it's the element, and when it goes to -2, we change the name to oxide. Okay, so the ion becomes oxide. Not only do we start changing the names, you can start putting these together, because when we start making compounds, think of it as 2 magnets, you know, the north and the south can come in and attract to each other. I got 2 north ends, not going to work. If I have a positive charge and a positive charge, they're going to repel each other, okay? try to jump start your car and reverse the cables, tell me what happens. It won't work, right? So we can start putting these together to actually start making compounds. For example, the magnesium ion. Now, when we start making compounds from the ions, we put them together such that we have enough positives and enough negatives to cancel their charge out. And if we need more than one, we start adding subscripts. This is where you could start putting subscripts. But let's take, for example, magnesium and sulfide. We can put them together to make a compound, simply MgS, okay? Which his name would be magnesium sulfide, okay? Not magnesium sulfur. Sulfur is the element by itself. Sulfide is the ion. It's only the ion that's going to come together and make compounds. Now, I can put lithium and sulfide together and make lithium sulfide, or I could put lithium and bromide together. Okay, because lithium has a +1 and bromide has a -1. I can put them together and I make lithium bromide. Okay, so here you're starting to put compounds together. I can do bromide, I can do chloride, I can do iodide. Okay, so right now you got a couple hundred compounds you can put together. And I just did lithium. You go to group 2 and start with beryllium, magnesium, calcium, strontium, and start putting them together. You can put a whole bunch of compounds together. Keep in mind, only the cation and the anion come together to make a compound, okay? And so we're going to be doing these later on because here I put the formula MgS, which is magnesium sulfide, and you could be given the formula and asked to name it, or you can be given the name and write the formula, okay? All right. So the term isoelectronic, I mentioned that before, it just simply means the same number of electrons. When the ions gain or lose electrons, they're going to be isoelectronic with some noble gas. So magnesium ion is isoelectronic with neon. They share the same number of electrons. If it's not neon, I can't overemphasize that. Magnesium ion, magnesium +2, did not become neon, okay? In order for that to happen, magnesium would have to lose some protons. Yeah. All right. Phosphorus becomes phosphide when it becomes an ion. It picked up 3 electrons, which is isoelectronic with argon, which is, if you look at the position of phosphorus, it is right before argon. And it's a non-metal, so it's going to gain electrons. Okay. So here we have the table that's asking you, what is the electron configuration of the calcium ion? And then it's asking you, well, who's it isoelectronic with? Okay. Now, we got calcium, and the biggest problem that happens here is one tends to forget to look at the superscript, and it's a charge. For the +2, that is an ion. So calcium has a total of calcium element. The atom has 20 electrons. But when it loses 2, now it has 18 electrons, hence the +2. Okay? Oxygen has a -2. The chloride, kind of hard to see, but that's a -1. And then the aluminum is a +3. Okay? So one way to do this is to write the electron configuration of the element itself, and then if it's a metal, remove whatever number of electrons you need to, and you have the ions. You have the electron configuration that you need. So here you can see, if you count the number of electrons, you got 6, 8, okay, 18 electrons, counting the superscripts for calcium ion. Oxide, notice I didn't say oxygen. I said oxide because I recognize there's a -2 up there, which makes it an anion. has 10 electrons. And then we got chloride, again, a negative charge. So the name is chloride, not chlorine. Okay. And the aluminum ion. That's how we don't change the name for the metal. And so the calcium ion is isoelectronic with argon, oxygen, isoelectronic with neon, chloride with argon, and the aluminum ion with neon. Now we can start putting compounds together. If I put calcium ion with the oxide, I have Ca capital O, calcium oxide. Okay, and we're gonna get more into that later on, putting compounds together. All right. Here they're asking you to figure out the number of protons, electrons, and neutrons. We have two different elements here. Se, which is selenium. We got to find it first. Okay. Anybody have an idea what the atomic number is for Se?
34.
34. Okay. So its atomic number is 34. Guess what? 34 is in group 6. Okay. 6 valence electrons. If it's 6 valence electrons, when it becomes an ion, guess what charge is going to be? -2. Okay. And so selenium would have 34 protons, 34 electrons, selenium atom, okay, the element, and 44 neutrons. The ion would differ only in the number of electrons because it picked up 2 electrons. It's in group 6. And so it becomes selenide. Sorry, got a little bit of a tongue twister there. So it's 34 protons and 36 electrons. Same number of neutrons. We didn't do anything to the neutrons. We're still dealing with 78, selenium 78. Okay. Aluminum 27. It is element number 13. So it has 13 protons. But they differ when they become ions because it lost 3 electrons and that has 10 electrons. When it becomes an ion, it still has 13 when it is the element. And then finally, neutrons is 14. All right. So tables like this tend to show up. Just keep aware of the mass number you're working with so you can calculate the neutron. The mass number is given to you up there. Remember the atomic notation is with mass number and superscript left. The atomic number is superscript right. There are some homework problems that give you the atomic notation. They give you about 4 choices, and you're asked to determine which one's correct. Well, keep in mind when you do that, do a process of elimination. First of all, make sure the symbol is correct because you always got to have a capital letter and a lowercase letter. There's 2 letters. And if they're both lowercase, then that's incorrect. Okay. Also make sure that the mass number is in the upper left and the atomic number is in the bottom right. And with that information, if you know, when you attack that problem, I think you should be able to select the correct answer. All right. That being said, guess what, guys? We're done with chapter 5. Okay. I've got a question here. Let me see. Okay, no problem. Daniel, yeah. All right. Now, what I want to do is I want to demonstrate how I use the periodic table to write out the electron configuration. Now, you can do it with that table that you were given before. Do we have? I don't think I have it here. Yeah, this one here. Yeah, you can use that table and memorize it if you want. 1S, use the arrow there. You start the 1S, then the 2S, then the 2P, 3S. You can do that, and if that works for you, great. Don't change anything if that's working for you. Okay. But I want to first. I want to share with how an alternative way to look at it. Okay. If it works, great. If it doesn't, that's okay too. Now, everybody has access to the periodic table, okay? So I would take it, download it, print it out, so you have a hard copy of it. Now, what I do immediately is I take it, and in the far left, I write the numbers 1, 2, 3, 4, 5, 6, 7. Those are what we're going to find out in the next chapter. They're called periods. They're the horizontal rows, okay? But they are also the energy levels for the electrons. We have 7 of them, okay? Whenever we discover element number 119, guess what? We're going to have 8, okay? But I don't know if it's coming around the corner pretty soon. Then the other thing I do is I go and refresh my memory. Remember we talked about, think of the ones in group 1 and 2 as the S electrons. So I make a note up there, S elements, I should say, not electrons. The ones inside, there's 10 columns. Think of those as the D elements, okay? And then starting with group 3A going across, there's 6 columns there. Think of those as the P elements. And then finally, down at the bottom, these elements, I wrote the number, the period number. They actually begin in number 6. So you see what 58? 58 is really in the 6th energy level, okay? But we pull them out to make the periodic table more legible and shrinking the periodic table. Now, this is the part that sometimes students have a little bit of a time with to grasp. Okay, let's take a look at element number 21. Let me zoom it up a little bit for you. Does that look a little better for you? All right. All right, so let's take a look at element number 21. Element 21 is in the D block, okay, which tells you that when I get to element 21, the D orbitals come into play. And if I shoot across from 21 all the way over to zinc, I can go say, to add those 10 electrons, I will just go D1 to D10. Plain and simple, right? All right. Now, here's the part that you have to remember. Element 21 is in the 4th period, but the D orbits, based on the mathematics of the equation, do not appear in the 4th energy level. They appear one level in, okay? So when you hit 21, you start with D orbit, but it's not in the 4th energy level. It is actually in the 3rd energy level. And so you take the period it's in and subtract 1. So that is 3D1 for element 21, okay? And if I went to element 39, it's starting the D electrons again, the D elements. It's in period 5. Its D orbits would be in 4D1. You follow? Just subtract 1 from the period. Now, going to the F. The F, starting with number 59, it is in the 6th energy level. But the F orbitals, what they appear in are 2 energy levels in. So they don't appear in the 6th. It wouldn't be 6F. It would actually be 4F. So you subtract 2 from the period it's in, okay? And it all has to do with the energy levels and the mathematics involved with those particular orbits, the D and the F. The S stay where they're at. The 1S is in 1S level, the 2 so on down the road. The P's stay where they're at. It is only the D's that they actually begin 1 level in from the period it's in, and the S begin 2 levels in from the period it's in, okay? So with that, let me clear this up a little bit. And let's just do calcium, okay? And so we're gonna do calcium. Okay, well, first thing I note is calcium is in the 4th energy level. Second thing I note is calcium is in the S elements. So I'm going to be using the s orbits at the 4th level. Third thing I know, it's in the second column. So I have 2 valence electrons. So right away, if I just wanted to write the valence electrons, I would say 4s2, okay? Because that's where it's at. But I want to write the whole thing. And so all the electrons, calcium has 20 electrons, and I got to start putting the electrons in the individual layers, starting with energy level 1. We're building it up. And remember, the order that the orbits get filled in, obviously is 1, 2, 3, and 4, but they go S, P, D, and F, okay? And so we're going to start, because we know that the first energy level is full. So of those 20, 2 electrons go in the first energy level. We know that there's only 1 orbital in the first energy level, okay? So then we got to go around the horn. We're going around the horn to the second energy level where lithium is. And so we go 2s2, that fills up the first 2 columns. We shoot across to boron, that starts to P. We know that in the second energy level, we have s orbit and the p orbit, starting with number 5. And so we're going to go all the way across and take care of 6 of those electrons. So we've got 6, 7, 8, 9, 10 electrons taken care of the original 20 from calcium. And so at this point, we are where neon is, okay? So now we go to number 11. Number 11 is full all the way across the board from the S to the P. So we go 3s2. We shoot across, that takes care of the electrons from sodium and magnesium. We go across to aluminum. That's where the P's start. So we're still in the 3rd energy level. And we go all the way across to 2p6. Okay. Now, we are across to argon. That should be 18 electrons at this point. I got 2 electrons to add. The only place they can go, obviously, is where calcium is, in the 4th energy level. And so that's 4s2. Okay, I wish I had the superscript period, but it doesn't support it. But I hope you can realize what I'm doing. The little up arrow is my superscript. So very quickly, just based on this position, we come up with the electron configuration of calcium. Now let's say, hey, let's go to number 21. Okay, 21 is part of the D element. So we start the D orbits, but just based on what I told you, when we get into the D orbits, they are 1 energy level in from the period it's in. So it becomes, guess what? 3D1 for element number 21. And if I continue all the way across to zinc, which is number 30, guess what? That's just the 10 up there. You see how it just fills up sequentially? And if I shoot across number 31, now I'm back to the P. So I go up to 31, I'm back to the P orbits, which are in the 4th period, 4th energy level. So that becomes 4p and 1. That's number 31. And if I continue across the periodic table to krypton, guess what I got to do? Just simply change that to 6. That is the electron configuration for krypton. Okay? All the way across. And if I wanted to go to number 37, okay, I'm adding here. You got a question? Let me see if I can answer it. Oh, when you add the 3. Okay. All right. The confusion is when you add the 3D. Okay. We started off with calcium. Okay. Calcium that is part of the S elements. Now, number 21 through 30 are what we call the D block or the D elements. That is where the D orbits come into play now, okay? But from, like I stated earlier, from an energy perspective, those D orbits are not in the fourth period as it was anticipated, because number 21 is in the fourth period, the fourth energy level. But it turns out that the D elements are actually one energy level in from the period that it occupies. So when you hit 21, when you hit the D element, the D orbitals, you subtract 1 from the period it's in, so it becomes 3D1. And as you go across to zinc, which is number 30, it becomes 3D10. You just go sequentially because there's 10 columns there. From number 21 to number 30, there are 10 columns, which represent the 10 electrons that occupy in the D orbits. Okay? And when you get into, say, number 39, if you got into 39, it also has D orbits because you're in the D block again. But they don't start in the fifth period. That's where number 39 is. They start one period in. Okay. Does that clear it up somewhat, Katrina? All right. Okay. And to not to confuse you, but when you get to the F, okay, looking at the period, when you get to F, which is number 59, 60, and forward, look at the period it's in. We'll start with number 6, but instead of going 1, go 2. So subtract 2 from the period it's in for the F orbitals. And so number 59 would have 4F1, or 4F2 here, okay? So the D elements, subtract 1 from the period it's in. The F elements, subtract 2 from the period it's in. And it's all related, again, to the mathematics of it. It was anticipated that they were expecting the Ds to be there in the fourth energy level, but based on the spectroscopic analysis, they came out, kind of surprising, 1 energy level less. And so we are across the krypton, and if you needed to go to 37, which is, 37 is in period 5, we will simply go 5S because it's part of the S block, 5S1. So you see how you can do that sequentially based on the periodic table, and remembering 1, to number the periods, 2, to recognize the S block, the D block, the F block, and the P block, and to remember that the D orbitals are 1 less, their energy level is 1 less the period they're in, and the F orbitals are 2 less the period they're in. And you just sequentially fill up the electrons, okay? All right. Does that make sense, or is it clear as mud? My suggestion is to take the periodic table and confuse, okay? Is either, okay, you're going to rewatch, okay. My suggestion is take your periodic table and label it like I just did, and then just pick an element, okay? And starting from the element, just write the electron configuration, okay? And if this method doesn't work, then follow the table that's on the slide, which directs you. This is the same thing I just went through, but here they're giving you the arrow going from right to left angle. 1S, you start at 1S, then 2S, then 2P, 3S, 3P, 4S, and then 3D, but 3D doesn't come into play until you see element number 21. and then 4P, okay, 5S. So, or it's written down there at the bottom of the sequence. So whichever works for you, that's the best scenario. Okay? I'm gonna rerun your brain. Okay. All right. Yeah, you said, well, you can print the periodic table. You have access to that. The periodic table is on the course website. Also, it is on the course website is also one of the things you in the beginning, the first module, very first module, I sent you to the periodic table and the shapes table. Okay, so you can print that out. Oh, you want to ask more information? But mine, the only thing I did was just add these numbers. I can send this out to you guys if you want. That'll be fine. Okay. Jackie has a study group. Is, okay, have you guys started a study group? You guys have a study group going on? Because you have access to WebEx, which is free. Zoom is good. You can get a Zoom, and if you get the free version, it allows you to do 40 minutes. But if you sign up with your EDU address, they did this for me for a while, they may take off that 40-minute break. But then you have, what else do you have? You got Google Meets, you have Facebook, right? Your Facebook friends. So, all right. What I was going to jump into 5, but you know what? Let me keep it kind of even. You guys are a little bit ahead, so I would practice on that configuration. The D's and the F's, not to worry about those so much. If they do show up, they might show up as like an extra credit or something like that. Okay, but if you work in the first 20, I think you'll be okay. Okay. All right. Any comments, questions, concerns? Why don't we leave it here, and we'll start with chapter 6, which is a very short chapter based on the periodic table, which is a lot of information already introduced to you. Okay. And don't forget, Thursday, I will be here at 5:30 instead of the regular 4:15. So if I'm a little bit late, hang loose, I'll get there. Okay. All right. Any questions, comments? Yeah. All right. Well, then I'll see you Thursday for those who come. Stay safe out there. All right. No questions? Because I'll go ahead and end it. No?
Thank you, sir.
All right. Thank you, guys. Thank you, guys. Stay safe.
Thank you.
You're welcome. Bye.